This is a road test of a Vishay MicroBRICK evaluation module. So let's open the box. This evaluation module number is a SIC 967EVB-A, and this is it here. So we have this PC board with the little MicroBRICK DC to DC converter on it, and we will be programming that with these resistors to be a voltage that we want, because this road test is a little bit different in the sense that I'm going to be using this in an application instead of just evaluating the performance as a standalone module. So I'm going to be building a power supply around this to actually run the camera that I'm recording this with right now. And what I want to do is have a continuous power source so that I don't have to worry about the battery running out. And this has plenty of power. It can produce 6 amps or supply 6 amps at whatever voltage we need. And there are some jumpers to select voltages, but I think I need one that's different, so that can be programmed with resistors here. Now I do have a battery eliminator type of cable for my camera, but the power supply that came with it has so much noise that it shows up in the audio track of the video. So that power supply is useless, and I need one that's quieter, and I think this one should do the trick. It's supposed to be a nice quiet power supply. So that's the reason why I wanted to apply for this road test, is to make sure this can work with a camera. Now, in order to do that, I'm going to turn it into more like a little bit of a power supply with its own case. So this is the 3D case that I printed. It has a GoPro mount on it, and there's slots for the power entry and the terminal block screws, and this thing fits in here really snugly. So there's some little rails in there.
Taking a look at the commercial battery eliminator power
of this
supply,
card in,
you can see that the noise exceeds 100 millivolts,
and it's gonna be very tight to slide it in. So let's just do that. That's all the way in, and it is not coming out. It's tight. The screws are available here, and the terminals are available on the front. Now this GoPro mount will mount onto a bracket that is on one of the tripod arms leading up to my camera. And I did make a cover for the back here, even though it's not necessary to hold the device in, but it slides across and keeps the dust out, etc. So a nice little power supply, and we're going to see how that works.
This is the Panasonic camera that is the target of this power supply project, shot with a Logitech webcam.
Okay, right up front we need to find out how much voltage and current this camera takes, and the nominal voltage for this battery is 7.2 volts, but when I'm running it from the power supply here, which is what it's plugged into right now, I need to run it at about 8.1 volts, and you can see that the current is 0.47 amps. So that's quite a bit of power. I did measure the voltage on the battery, and it is over 8 volts, but it's nominally only 7.2. However, this means that I need to set the power supply voltage to something like 8.1, 8.2. The maximum voltage for the battery, I think, can be about 8.4 volts, and it discharges down to its nominal value, but it appears to need more than 7.2 volts, so it is running fine at 8.1 volts. And we'll just have to use that to set our voltage for our Vishay power supply.
But let's look at noise.
This is what the waveform looks like when I am just not filtering, and this is what it sounds like with some noise on it. You may be able to hear the noise if you increase the volume of your audio. And here's the same noise, looks the same, and we're just listening to see if there's the same kind of noise in the audio trace as well. But there's a lot more capacitance on the output of that power supply.
This is the commercial battery eliminator power supply that I bought, showing that it has over 100 millivolts of noise. Now taking a look at the MicroBRICK, we can see that the noise is down around 3 or 4 millivolts, which is perfectly adequate, and I don't think we're going to hear any noise.
Okay, now I want to figure out how much voltage drop there is in this cable. So this is the fake battery, which allows me to use a power supply instead of a battery, so I can plug this in where the battery goes. Now I want to know how much voltage drop there is in the cable, because this power supply was saying I need 8.1 volts when the battery nominal voltage is 7.2. So let's just see. What I'm going to do is I'm going to set the power supply up for 0.47 amps current limit, and then I'm going to short the two terminals here and just see what voltage the power supply reads. So let me just stick this in a little vise so I can... Okay, I'm going to try and short this out. Hopefully we can see the power supply at the same time. So 0.15 volts. Which means that this thing needs about 7.9 to 8 volts right at the battery terminals. Okay, so that means I need to set this module up for 8 volts or better. Probably 8.1 is a good number, or 8.2. So I need to do a little calculation to figure out what resistor I need to install there. It's an 0603 resistor. Unfortunately, I don't have a stock of those, so I'm going to have to figure something else out. But once I've done that, I'll get back on this video.
The MicroBRICK has several configurable options, and this is how I set it up for my application. So underneath the card I replaced R6, which was 43K, with a 68K resistor. This allows the input voltage to be reduced from something over 35 volts to around 12 to 13 volts, and it also makes the undervoltage lockout around 11 volts. J2 is open, which sets the maximum inductor valley current limit to 7.5 amps. The R10 resistor was 43K, and now I have changed it to 94K, which gives me about 8.2 volts output. The J1 mode selector is set to mode 2, which sets it to an internal LDO and turns the power save off. J7 is set to 100%, which actually means that the maximum valley current limit is not connected. J3 is set to the B position, which is a 1 megahertz oscillating frequency for the power supply. J5 is in the first position, which selects the resistor programmed to 8.2 volts. One thing I noticed is that the input voltage needs to be 4.1 volts above the output voltage in order to get full regulation. With all the setup options in this module, you do need to take a little bit of time to go through and figure out exactly what you need and how to configure it. But once you've got it dialed in, it works great. Now to assemble and test.
This is a quick test to see if there's any audible noise from this power supply. I can't show you everything because it's plugged into the camera right now, which is taking this picture, but there's the 12 volt power supply feeding up to the Vishay DC to DC converter, which is generating about 8.4 volts for the camera. And this is the tripod where it's going to get mounted, so here we go, and that's how it works. Done.